We are the University of Michigan team, and in this presentation, we will discuss curb space management for multimodal transportation in downtown areas with collaboration from MDOT in the City of Ann Arbor. First, we will introduce some background information along with why we chose our subject area. Next, we will describe the existing conditions of the subject area. Then we are going to describe the two proposed solutions and then end with a summary. Curb space has multiple uses, such as on-street parking, loading zones, bus stops, bike paths, pickup and drop-offs for ride-sharing services. Some of these uses have been managed throughout history, but as we're getting new modes of mobility, we need to start planning them into our curb space. Pictured is downtown Ann Arbor in early 1940, and you can see that the curb space here is mostly used for parking. Curb space has been managed since the 40s through time limits and pricing schemes, which help balance the supply and demand of customer on-street parking and to help promote turnovers. Downtown Ann Arbor was chosen to be our subject area due to the fact that it's the 5th largest city in our state. Also, Transportation for America launched their Smart Cities Collaborative within the city. And lastly, the high housing prices of Ann Arbor help to promote that downtown workers live in neighboring cities and commute in. In fact, 80% of the Ann Arbor workforce commutes to work, making the city's curb space highly valuable, as you can see in this photo of Main Street with all the on-street parking occupied. The 2017 traffic counts of daily commuters coming into Ann Arbor was more than 42,000, and 42% of these vehicles are driving alone to work. Commuters are using residential parking and on-street parking meters. This is decreasing the on-street parking and turnover rates and impairs the accessibility to curb space for different modes of transportation. On-street parking spots during 6 p.m. to 9 p.m. are highly occupied by customers who need to have quick access to their businesses. The difficulty in finding a parking space leads to longer cruising times, and it also adds to the already congested downtown. Therefore, the city needs to regulate the occupancy rate during the weekday evenings. The occupancy of on-street meters during the day needs to be leveraged to about 70% to achieve some of these new mobilities so that we can start allocating the curb space to the new stakeholders. A new demand for accessibility to curb space, for instance, are spin scooters in Ann Arbor. These scooters cannot just be parked anywhere. Specific parking spaces should be planned within our curb space. Another example would be Lyft. These vehicles need curb spaces to rest and to pick up and drop off their passengers. Currently, the Ann Arbor Downtown Development Authority oversees the management of parking spaces and manages about 1,000 on-street spaces and 5,000 off-street spaces, which totals to about 6,000 spaces in the city of Ann Arbor. Optimization of curb space occurs at the equilibrium point where the supply and the demand curves meet. We identified 3 sets of solutions to change the driver's use of curb space in downtown Ann Arbor. We distinguished our solutions by whether they improve the use of the available curb space supply or lower the demand for it by offering alternative options.
The first set of solutions that we would discuss would be the supply-focused solutions. Under these solutions, our main objectives are to expand the supply of parking in the network by reserving locations for right-sourcing parking, making locations that were underutilized or underused more appealing. We propose to accomplish this through 3 means. The first means would be to, based on the use of right sourcing and other curb space demands throughout the day, we would be able to identify flexible use zones and then use dynamic information boards to communicate this to the community. Secondly, we would look into upgrading our infrastructure to support the smart parking system that we would put in place. The system has already been deployed in a lot of cities around the United States, which would include Los Angeles, San Francisco, and New York, to name a few. Through this, the system would then know the available parking spaces and could navigate the users directly to those spaces. Finally, to make previously undesirable parking locations more appealing, we can make use of smart mobility scooters to cover the first and last mile between the user's undesirable parking location and their final destination. In terms of a functional architecture for our solution, the 3 main stakeholders for this process would be the drivers, the parking management system, and the back-end infrastructure that is supporting all of these services. The parking management system takes data from the connected vehicle growth set equipment, as well as the personal information devices of the users who are making use of our parking system. Making use of the data that it collects from these 2 devices, it is then able to guide users to the right set of parking locations and also allow us to efficiently make use of the smart mobility systems as well as the smart mobility scooters that we have in use. In terms of a cost breakdown and a timeline for the deployment of our solution, we foresee that the total cost of the solution would be about $137,000. This would include the roadside signs, the smart parking in-ground sensors for the parking monitoring system, the traffic information dissemination software for us to analyze our software and derive insights, and then our smart mobility scooters for covering the first and last mile from the undesirable locations to the final destination. This cost becomes even more attractive when you consider that the total population of Ann Arbor is about 113,000, and about 30 to 40,000 people are commuting into the city every single day, which is increasing the population of the city by about 30 to 40%. And this means that the total cost for the solution would be about $1 to $1.2 per person. In terms of the timeline for the solution, we foresee that it would take about 10 months. It would start with the stakeholder meetings, which would then be followed by a public hearing. After this, we would collect data for the on-street parking and its demand. This would allow us to make flexible zones decisions, after which we would be able to construct the infrastructure construction. And then finally, we would have our trail operation.
So providing vehicle aging tools to find parking can only solve the problem of the uneven utilization distribution. However, it could not help reduce the demand for curb space parking. Therefore, we recommend two demand-focused solutions, incentivizing people to choose the multimodal transportation options and the dynamic pricing. In order to increase the multimodal transportation options, we could provide a shuttle system for commuters and priority parking for carpooling program participants to reduce the demand for curb space parking. Besides, we can promote the non-automotive transportation modes accessibility and convenience by promoting greener transportation modes, such as scooters, to encourage people to choose the off-street parking by covering the last mile of their trips. The key point of the architecture is to promote the information share among different stakeholders. The Transit Management Center will collect the parking information from the parking management system, receive, coordinate, and send out the transit-related information, and could adjust the transit service plans for certain events, such as football games, based on the information received from the event coordinators. The cost is for implementing a shuttle service, including the cost of purchasing the shuttles and the operational cost. The solution could be implemented in 8 months. The nature of the task involved is similar to the supply-based solution. If we consider the curb space occupancy, we can see from the table that the nighttime off-street occupancy of Carytown is much lower compared to other sub-areas, which illustrates an uneven parking distribution. Cities around the U.S. have adopted the dynamic pricing to solve this problem and could be a good reference for us. The key point of the dynamic pricing is to select the correct price for the city, and therefore refer to the previous experience. We'll adopt the parking price elasticity to adjust the parking occupancy to 85% for the 4 sub-areas, which is highly recommended by cities who have implemented the dynamic pricing. So based on the statistics, we set the pricing standard as following. We also intend to apply the roadside loop detectors and video cameras to monitor the curb space occupancy and adjust the meter rate based on the following standard. The parking management system associated with the connected vehicle roadside equipment could monitor the curb space occupancy and adjust the meter rate in time. The vehicle OBE will communicate with the payment device and the parking management system to update the real-time parking information. The parking management system will send out the payment instructions to the Payment Administration Center. The Payment Administration Center will send out the payment request to the personal information device, and users can make payments using their mobile phone. The cost is used mainly to build a software for the dynamic electronic billing and pricing, and also to collect the on-street parking data.
So here is a quick summary. The curb space management has been an issue for a long time. To optimize the usage of curb space, we propose 2 sides of solutions. First, provide smart infrastructure and smart vehicle aids that could help adjust the curb space parking distribution. Second, use economic lever and alternative substitute to reduce the curb space parking occupancy and instead increase the accessibility of multi-transportation modes to the curb space. In a city, we could use any combinations of those solutions. And with that integrated multifaceted solution, the coordination among different transportation agencies is a key point. And that's all for today. Thank you for your listening.